In this lesson, we're going to take a look at empirical and molecular formula. So in our last lesson, we looked at percent composition, which gave us the percent of mass of a compound that came from each of the different elements that make up that compound. So a molecular formula, on the other hand, is the formula of a compound that gives how many atoms of each element there are, so the number of atoms as opposed to a mass. And the empirical formula is the lowest terms ratio of atoms of each element in a compound. So we've talked about how all ionic compounds are simply a lowest terms ratio of how many atoms of each element are present there. So C4H10, I have a 4:10 ratio. That is not lowest terms, so that's a molecular formula. C2H5, 2:5, I can't reduce that any, so that is lowest term, so that's empirical. And C2H5 is the empirical formula of butane, so this is the molecular formula, and then the empirical formula is C2H5 for lowest terms. Glucose, C6H12O6, 6, 12, 6 can all be divided by 6, so that's molecular. And if we were to divide each of those by 6, we'd end up with a 1,2,1, or CH2O, which is the empirical formula for glucose. H2O2, is that empirical or molecular? So 2:2, that can be reduced, which makes it a molecular, and 1:1 is the lowest terms ratio, so HO would be the empirical formula for hydrogen peroxide. So at this point, you can pause the video and try each of these on your own. So water is a 2:1 ratio. That is lowest term, so that is an empirical formula. We also know, though, that H2O is the formula for the compound water, so that is also a molecular formula. CH4 is the compound methane, so that is molecular. 1:4 is a lowest terms ratio, so it's also an empirical formula. C2H4 is ethene, which is the molecular formula, and 2,4 is not lowest term, so it's not an empirical. C5H10, or pentane, so that's the formula for pentane, and that is not lowest terms, 5-10, so 1-2 would be a lowest terms for that. And CO2, we know that that is the formula for the compound carbon dioxide, but it is also a lowest terms ratio, 1-2, so that is also an empirical formula. So to calculate an empirical formula, we can use percentages and molar masses and then a ratio to calculate the empirical formula. And we'll go through an example of that to show each of the steps. So an oxide of aluminum is found to contain 52.93% aluminum and 47.07% oxygen. Calculate the empirical formula. So for our solution, we can set up a table to find the mass of each we would have in 100 grams, figure out how many moles of that element that would be, and then figure out a mole to mole ratio. So if I have 52.93% and 47.07%, I can pick any number as my sample and then calculate 52.93% for aluminum and 47.07% for oxygen. To make it easy, if I pick 100 grams, then my percent is also just going to equal my mass. So 52.93% of 100 would give me 52.93 grams of aluminum, and 47.07% of oxygen would give me 47.0 grams of oxygen. So the first thing we will do then is that. So once again, simplest if we use 100 grams, because then the percentage is going to give us the exact mass. So now we want to solve for how many moles of aluminum are in 52.93 grams. So if you recall, to calculate a number of moles, we are just going to take the mass and divide by its molar mass. So aluminum's molar mass, if we look that up in the periodic table, is 26.98 grams per mole. So this is using a strategy that we will use later on, but if you prefer here to solve by doing number of moles equals mass divided by the molar mass, you are welcome to do that. So this essentially ends up being a division. So I have 52.93 times 1 divided by 26.98. So you can do either or, whatever you feel better about. This is using units to help you get to your final answer. So we're looking for an answer in moles. I have a mass. My molar mass will give me mass and moles. So I want my grams to cancel out, and then I'm going to be left with moles as my answer. So 52.93 divided by 26.98. So that gives me 1.962 moles of aluminum. For oxygen, I have 47.07 grams. The molar mass is 16 grams per mole of oxygen. So that gives me 2.942 moles of oxygen. So I can fill that into my table. And now I need to solve for my mole ratio. So what is the ratio of this number to this number? Now this is not very easy to see here because they're not whole numbers. So it's not easy to see the ratio. So what I can do to convert these to whole numbers is to divide both of them by whichever the smallest one happens to be. So in this case, that is 1.962. So I can divide both of these by that number. And that gives me 1 for aluminum. And for oxygen, that gives me 1.5. So that isn't a whole number ratio. I can't have 1.5 atoms of oxygen. So what I'm going to do is, that is a half, which is 1 over 2. And so if I multiply both of these by 2, then that would get rid of the fraction a half over there. So that then gives me a 2 to 3 ratio for aluminum to oxygen, which means that my formula is 2 aluminum to 3 oxygen, or Al2O3. So we'll look at another example. So nylon 6 has 63.38% carbon, 9.8% hydrogen, 12.38% nitrogen, and 14.14% oxygen. So we're going to calculate what the empirical formula is. So we know it has C, H, N, and O. So step 1, we're going to calculate the mass of each element in 100 grams. Now remember, that is just, if we do it in 100 grams, it's just whatever the percent is, but in grams. Then we are going to take those masses and convert to moles by dividing by the molar mass. So carbon, I had 63.38 grams of it. Molar mass is 12.01 grams per mole. So this will cancel the grams of carbon and leave me with moles of carbon, which is 5.277 moles. For hydrogen, I had 9.8 grams. 1.01 grams per mole is the molar mass, and that gives me 9.703 moles of hydrogen. 12.38 grams of nitrogen I had, and molar mass is 14.01 grams for nitrogen, and then that will cancel my grams of nitrogen, leaving me with 0.8837 moles of nitrogen. Last one was oxygen, 14.14 grams of oxygen, and 16 grams per mole is the molar mass there, and that calculation leaves me with 0.8838 moles of oxygen. So now what I want to do is I want to find a whole number ratio. So I'm going to take each of these and divide by the smallest one, which is 0.8837. So I'm going to take each of those and divide by 0.8837, which leaves me with 5.971 moles of carbon, 10.999 moles of hydrogen, 1 mole of nitrogen, and 1 mole of oxygen. Now these are close enough to whole numbers that at this point it's okay to do some rounding. So here I can round. Now we are only talking about rounding if I am into the hundredths away from being a whole number. And so this doesn't even register when I am going to 3 decimal places. So these ones were fine. This one, 10.999, that can easily round. And here, 5.9, so we're into the hundredths before we are off. So my ratio of carbon to hydrogen to nitrogen to oxygen, 6 to 11 to 1 to 1. So I have C6H11NO for my empirical formula for nylon. Okay, so here we are actually going to be looking at molecular formula, and we're going to use empirical formula to help us with that. So a white powder is analyzed and found to have an empirical formula of P2O5. So that's the empirical formula. The compound has a molar mass of 283.88 grams per mole. So we want to find out what the compound's molecular formula is. So it's P2O5, and then we would have to multiply the 2 and 5 by something. So that's in a lowest terms ratio. So the first thing we're going to do is figure out the empirical formula mass. So what is the molar mass of P2O5? So I have 2 moles of phosphorus atoms at 30.97 grams per mole. So 61.94 grams for the 2 moles. Oxygen, 5 times 16 grams per mole. So 80 grams per 5 moles of oxygen. And that gives me a molar mass of P2O5 of 141.94 grams per mole. Now the molar mass of the actual substance is 283.88. So I have so many units of P2O5 that will give me 283.88. I know that P2O5, 1 unit of that, gives me 141.94. So if I take the molar mass that I'm given and divide by that empirical formula mass, then I can figure out how many units of P2O5 are in the actual compound, and that division tells me 2. So now I'm going to multiply that. So I have 2 units of P2O5, which would be P4O10. So that is the molecular formula for the compound. The empirical formula for that was P2O5. We'll go through one more example of that. So a compound is found to have an experimental molar mass of 78 grams per mole. The empirical formula is CH. What's the molecular formula? So once again, we're going to look for the molar mass of CH. So 1 carbon, 1 hydrogen. We add that up, 13.02 grams per mole. So every unit of CH has a mass of 13.02 grams. I have 78 grams. So now I need to figure out how many units of CH are in that 78 grams. So 78 divided by 13.02 gives me 6. So I have 6 units of CH, or C6H6.